Welcome to Balancing Oxidation-Reduction Equations. So, we need to talk about oxidation states. So chemical reactions in which the oxidation state of one or more of our substances change are called oxidation-reduction reactions. These are redox reactions. So remember that oxidation involves a loss of electrons. We can say oil rig. So oxidation involves losing electrons. Reduction involves gaining electrons. So electrochemistry is that branch of chemistry that deals with relationships between electrochemistry, between electricity and chemical reactions. So changing electrons. So let's consider the spontaneous reaction that occurs when zinc metal, zinc solid, is added to hydrochloric acid. So hydrochloric acid is going to dissociate, so we have zinc plus hydrogen. We get the zinc loses 2 electrons, and the hydrogen, each of the hydrogen ions gains 1 electron to now make hydrogen gas. And the oxidation numbers of our zinc and hydrogen have changed. The oxidation number of zinc has increased from 0 to +2, and the oxidation number of hydrogen has decreased from +1 to 0. So this means that the zinc is oxidized because it's losing electrons, and the hydrogen is being reduced because it's gaining electrons. So this means that hydrogen is causing zinc to be oxidized. So hydrogen is the oxidizing agent, or the oxidant. And zinc is causing the hydrogen to be reduced, which means the zinc is the reducing agent. So note here that the reducing agent is oxidized and the oxidizing agent is reduced. Remember the law of conservation of mass. The amount of each element present at the beginning of the reaction must be present at the end. We're not allowed to change the number of atoms of an element. The law of conservation of charge says that electrons are not lost in a chemical reaction, they have to go somewhere. And some redox equations can then be easily balanced by inspection, but some of them, or for many of them, we need to look carefully at the transfer of electrons in order to balance our equation. So we're going to break them up into half reactions because this is a convenient way of separating our oxidation and reduction reactions. So let's look at this reaction. We have tin 2 plus 2 iron 3 yields 1 tin 4 and 2 iron 2. So the oxidation half reaction is the tin going from tin 2 to tin 4, but we have to have a balanced charge. Here we have a charge of 2 plus, here we have 4 plus, so we need these 2 electrons to balance off the charge. And this is basically showing that 2 of our electrons have left the tin 2 and they're going somewhere else. So basically the electrons are acting as a product. Here, our reduction half reaction, we've got 2 iron 3 ions are reacting with our 2 electrons to give us 2 iron 2 plus ions. And again, here note that the electrons are acting as a reactant. So let's look at the titration of an acidic solution of sodium oxalate, which is colorless, with our potassium permanganate, which is a deep purple color. The permanganate is reduced to manganese 2, which is this pale pink, while our oxalate is oxidized to carbon dioxide. So our equivalence point here is then indicated by the presence of a pale pink color, where we're showing up our manganese ion there. And if we add more potassium permanganate, then the solution will turn purple because of an excess of our potassium permanganate then. So what is our balanced chemical equation for this reaction? I want you to pause the video and find out. Write it down. So we can determine this using the method of half reactions. So we'll write down the 2 incomplete half reactions. So we have the permanganate reacting to give us manganese 2. We have the oxalate reacting to give us CO2. Now these are clearly not balanced. We don't have the same number of oxygen atoms on each side. We don't have the same charge on each side. So we need to do some work. So let's balance each half reaction. So first let's balance the elements other than hydrogen and oxygen. So here we don't need to make any changes because the number of manganese atoms is the same. Here, we need to put a 2 in front of CO2. So we've done that. Next, we'll balance oxygen by adding water. So we need to add some waters to this side. We have 4 oxygen atoms on that side, so we need 4 waters on this side to balance that. In this case, after we added that 2, now we have 4 oxygens on this side and 4 oxygens on that side, so that one's already balanced for oxygen. So now we want to balance the hydrogen by adding protons, H+. So we put H+ on that side, and we need 8 of them because we have 8 hydrogen atoms on this side. Down here, it's already balanced for mass, but not for charge. So now we want to balance the charge by adding electrons, and we'll write the overall charge on each side. So here we have 8 times positive 1 plus 1 times negative 1. That's giving us 1 times positive 2 plus 4 times 0. So we have positive 7 going to positive 2. And over here, we have negative 2. So it's 1 times negative 2, and that's giving us 0. So now we want to add in electrons. So we need to add 5 electrons there to balance it out. And here, we need to add 2 electrons on the product side to balance it out. And now we're going to multiply each half reaction to make the number of electrons equal. So the lowest common multiple of 2 and 5 is 10. So we need to multiply the top one by 2, the whole equation. And we're going to multiply this whole bottom equation by 5. And that means that now we have 10 electrons plus 16 hydrogens plus 2 permanganate yields 2 manganese ions plus 8 water molecules. And then we've got 5 oxalate ions yields 10 carbon dioxides and 10 electrons. And now we can add our reactions together. So we've got 10 electrons here and 10 electrons there. So let's cancel those. Let's see, does anything else cancel? Nope, nothing else cancels. So now the reaction is balanced. So all of our electrons have canceled out. We used up 10, we produced 10, and our charges are now balanced left and right. So to balance the equation for a reaction in basic solution, we use the same method as above, except hydroxide is added in order to neutralize the hydrogen ions used. And here, then the equation must again be simplified by canceling our like terms of on both sides of our equation. So that was balancing oxidation-reduction reactions, balancing redox reactions.